All right, we had a sound glitch on recording the first part of this review session, so this is take 2 of part 1 of our exam number 2 review session. First, I'll say a few words in general about exam number 2. It will be the same format as exam number 1. We're going to have 20 multiple choice questions worth 3 points each, and anywhere from 5 to 7 short answer questions worth the remaining 40 points. Those short answer questions are going to be identical in format to short answer questions we had on exam number 1. There will be questions where you're asked to predict the products of a reaction, and you want to pay particular attention to stereochemistry when that's applicable. There will be questions where you'll be asked to provide reagents for certain transformations. There will be questions where you're asked to draw mechanisms, okay, and make sure you don't skip steps. Make sure you use your curved arrows properly. And then there will be a synthesis question. And so no surprises in terms of the format. Advice for studying for this exam: you want to focus on understanding rather than memorizing as much as possible. There is some memorization. There are some principles that we weren't able to explain that we did memorize, such as in a Wittig reaction where a normal ylid will give a Z product, whereas a stabilized ylid will give an E product. So there are some things we memorize, but most things we've taught you, we explained why those principles affected reactivity the way that they did, or why a reaction would occur in one way or not another. And so if you understand the underlying reasons why, that minimizes the amount of memorization that you do, and therefore minimizes any chances that you might get the facts mixed up when you go into the testing center to take the test. So things like relative reactivity of carboxylic acid derivatives, relative reactivity of reducing agents, those sorts of things you shouldn't memorize, but you should understand the underlying principles, okay? And that will save you. Even though there's a ton of reactions in this section of the class, they really fit into, in the vast majority of cases, 2 general categories. We have our nucleophilic addition reactions to aldehydes and ketones, and we have our nucleophilic acyl substitution reactions with our carboxylic acid derivatives. So even though we have a lot of reactions, they really all fit into these 2 categories, and they have a lot of common steps. In the mechanisms, we have nucleophilic addition steps, we have elimination steps, we have proton transfer steps. And so if you learn them based on what they have in common, then it's a lot easier than treating all of the reactions and mechanisms as unrelated to each other. Okay? All right, so with that, let's go into a discussion of specific topics in chapters, starting with chapter 20, our introduction to carbonyl chemistry, where we learned about organometallic reagents, and we learned about oxidations and reductions. So we started off with the structure of the carbonyl group and how that structure influences its reactivity. We said that the carbonyl group is trigonal planar. That makes it less crowded, less sterically hindered than a tetrahedral carbon. We said that it's electrophilic at the carbon because of the polarization of the bond towards oxygen. And we said that the pi bond is easily broken. And so these 3 features of the structure of the carbonyl group impact its reactivity. We classify our carbonyl compounds into 2 groups. We have aldehydes and ketones in one group, and aldehydes and ketones undergo nucleophilic addition reactions, okay? And then we have our carboxylic acids and their derivatives. Carboxylic acids and derivatives, those undergo nucleophilic acyl substitution, okay? Because we have a leaving group attached to we refer to it as the Z group, attached to the carbonyl carbon of a carboxylic acid. That allows it to undergo nucleophilic acyl substitution. Okay? We talked about the relative reactivity of these compounds. Okay? In a couple different ways. We said that aldehydes and ketones are more reactive than our carboxylic acids and their derivatives. Those Z groups are donating electrons to the carbonyl carbons, and therefore making them less reactive. We also talked about how aldehydes are more reactive than ketones. We gave two reasons for that, a steric reason and an electronic reason. And then we didn't talk about it in this chapter, but in chapter 22, we talked about the relative reactivity of our carboxylic acid derivatives, depending on the basicity or the electron donating ability of the Z group. So that's a topic we'll have more to say on when we get to chapter 22. Okay, so we talked about reactions of these carbonyl compounds, and we started with reductions. And we started with the reductions of aldehydes and ketones. Okay? And we learned about some metal hydride reducing agents. We learned about sodium borohydride, and we learned about lithium aluminum hydride. We learned that lithium aluminum hydride is more reactive than sodium borohydride. You should understand why that is the case. We explained it in class. Because of that difference in reactivity, sodium borohydride can be dissolved in methanol. It reacts very slowly with that protic solvent. Whereas with lithium aluminum hydride, we've mentioned several times that you have to add water in a separate step to reductions with lithium aluminum hydride. Okay? So in these reductions of aldehydes or ketones, we also talked about the reduction of enones. Remember, an enone is an alpha beta unsaturated aldehyde or ketone where we have an alkene conjugated to the carbonyl group. And so you should know the different ways of reducing enones. We can reduce them where we only reduce the carbonyl group. We can reduce them where we only reduce the alkene. And then we can reduce them where we reduce both the alkene and the carbonyl group. And you should know the reagents that will accomplish those reductions. Then we talked about enantioselective reduction of ketones. When we reduce a ketone that is not symmetrical, where the two R groups attached to the carbonyl are different from each other, we form a stereocenter. We form a chiral secondary alcohol. With our achiral reagents, we form a racemic mixture. But if we use a chiral reagent, a chiral reducing agent, then we can perform an enantioselective reaction that gives us a major enantiomer and a minor enantiomer. And the reagent we talked about was the CBS reagent. Okay? Now, please don't memorize the structure of the CBS reagent. Please don't memorize the mnemonic device in the book that tells you which enantiomer of the reagent will give which enantiomer of the alcohol. That's not very valuable in my opinion. What's valuable is understanding how it's possible to obtain a major enantiomer and a minor enantiomer in that reaction. Okay? We discussed that last semester in the context of the Sharpless asymmetric epoxidation, and we gave the same explanation this semester in discussing chapter 20. Namely, we drew an energy diagram on the board with pathways leading to both enantiomers. The transition state leading to the major enantiomer is lower in energy than the transition state leading to the minor enantiomer. And we mentioned in class that those transition states are diastereomers of each other. That's why they're different in energy. So that general explanation of how it's possible to obtain a major enantiomer and a minor enantiomer is much more important than understanding which enantiomer or which isomer of the reagent gives which isomer of the alcohol. Okay? Nature performs enantioselective reductions of ketones, and it uses NADH as its reducing agent. Okay. You don't need to know the structure of NADH. It's a very large molecule. But if we gave you its structure, you should be able to draw the mechanism of NADH reduction. It's simply the reverse of NAD plus oxidation, which we learned last semester. Okay. Next thing we talked about was the reduction of carboxylic acid derivatives. Okay. And in this section, we learned about two new reducing agents, Dibol and lithium tritert butoxy aluminum hydride. We said that these reducing agents are more reactive than sodium borohydride because sodium borohydride is a borohydride and these are aluminum hydrides. But these reagents are less reactive than lithium aluminum hydride, and you should understand why. That's something we went over in class. So these reagents will react with acid chlorides and esters to afford aldehydes. But something we talked about in class that was not in the book is that low temperature is required for these reductions, okay, minus 78 degrees. You should understand why that is the case. We also went over that in class, okay? Then we talked about the reduction of carboxylic acids and amides. So these reagents will reduce esters and acid chlorides, but not carboxylic acids and amides. For carboxylic acids and amides, lithium aluminum hydride is required. Okay? Carboxylic acids and amides have an OH and an NH respectively that is deprotonated by the lithium aluminum hydride in an acid-base step. And then the mechanism proceeds from there. So you should be able to draw the mechanisms of reductions of acids and amides. We drew it in class. There's kind of a funky leaving group. It has a dianion, a negative charge on an oxygen, and a negative charge on an aluminum. But remember, the negative charge on the aluminum is spread out. Okay. And then the other thing to remember is that when we're reducing amides, the nitrogen doesn't leave. We retain the nitrogen in the product. So reducing an amide gives us an amine as the product, whereas reducing a carboxylic acid gives us a primary alcohol. So there's a summary table of these reductions. It is table 20.1. And again, you shouldn't memorize the information in the table. You should understand the outcomes. You should understand why reacting a given reducing agent with a given carboxylic acid derivative or an aldehyde gives the product that it does. Okay, so if you understand the material in this table, you'll know that you're well prepared to take the exam. All right, we briefly talked about oxidation. Oxidation of aldehydes to carboxylic acids. Okay, and that oxidation is known as the Tollens oxidation, where we use silver oxide and ammonium hydroxide in that reaction, okay, known as the Tollens reagent. That's the one that gave the silver mirror that I did that reaction in class. Okay. So then the remainder of the chapter we spent focusing on organometallics. The first part we focused on our metal hydride reducing agents. And then the rest of the chapter we learned about three different types of organometallics with carbon metal bonds, our organolithium reagents, our Grignard reagents, and our organocuprates. Okay. You should know the relative reactivities. We said that these two are comparable, but our organolithium is the most reactive. Our organocuprates are the least reactive. And that's related to the electronegativities of those metals, okay? So that's something you should understand rather than memorize. The preparation of these compounds is also important to know. We just start from alkyl halides. In these cases, we just add the metal or the metal chloride salt. Well, actually, we add the metal in both cases to the halide. Here, it's a little bit more involved. But the preparation of the reagents is something you should be able to do. We talked about how organometallics are basic. They will deprotonate OHs and NHs. Usually we don't want that to happen, but there's one case in which it can be useful. We said that we can take an alkyl halide, we can convert it into an organometallic, either a Grignard reagent or an organolithium reagent, and then we can treat that reagent with water. It will deprotonate water. So that's how we can make an alkane from an alkyl halide. If we need to reduce an alkyl halide, that's one case in which the basicity of that reagent is useful, okay? But in cases where it's not, where we don't want the basicity to interfere, that's where we need to use protecting groups, as we'll mention in a moment, okay? So let's talk about the reactions of organolithiums and Grignard reagents first. They're similar in how they react. They have comparable reactivity. And they react with aldehydes and ketones to generate alcohols. We form secondary alcohols from the reactions of aldehydes with these reagents, tertiary alcohols from the reactions of ketones with these reagents. These are very important reactions because they involve formation of a carbon-carbon bond. They allow us to make longer chain alcohols from shorter chain aldehydes or ketones and these reagents. So these are very useful reactions in terms of synthesis. But as I mentioned, if you have an acidic hydrogen, either an OH or an NH somewhere in the molecule, instead of performing this reaction, your Grignard reagent or your organolithium will simply perform acid-base chemistry. And so when you don't want that to interfere, you have to use a protecting group to block that OH temporarily, okay? So we introduced the concept of protecting groups, masking one functional group so you can react another functional group. And the protecting group we used for alcohols was the TBDMS ether. It's a silyl ether, tert-butyl dimethyl silyl ether. You should understand, you should know the conditions for installing that ether, that silyl ether, as well as the mechanism of that process. It's closely related to the Williamson ether mechanism. We went over it in class. You should also understand the deprotection conditions for cleaving the silyl ether and restoring the alcohol. That's an SN2 type reaction using fluoride as the nucleophile. And the reason that works well is that the fluoride silicon bond is a very strong bond, okay? So protecting groups, in this section of the class, it was the TBDMS ether, which is a silyl ether. All right, our organolithiums and our organomagnesiums will react with esters and acid chlorides. But they do so twice. They react once by a nucleophilic acyl substitution to give a ketone intermediate. And then that ketone intermediate is more reactive than the ester or acid chloride that we started with. So they react twice, and they generate tertiary alcohols. Right? So two equivalents of the R group from the Grignard or the organomagnesium or the organolithium is present and forms that alcohol. We can't stop at the ketone. But we do have a way of making ketones from acid chlorides. And that's using our organocuprates. So the next thing we learned was that organocuprates plus acid chlorides, which I'll draw out like that, gives ketones. This reaction follows a different mechanism. Our organocuprates are less reactive than our Grignards and our organolithiums, so they can react by different mechanisms. That different mechanism allows it to stop at the ketone. This was one of the mechanisms we did not learn, though, so we just have to memorize the outcome of this reaction. Okay? We learned about Grignard reagents and organolithiums reacting with carbon dioxide. That generates a carboxylic acid with one more carbon in the chain than the original organometallic species. And we have to add acid in a final step to form that carboxylic acid. Okay? Epoxides are the one type of electrophile that all three of our organometallics will react with in the same way. They will all perform ring opening of epoxides, and that's going to be the SN2 ring opening of epoxides, which proceeds by backside attack on the less substituted carbon of the epoxide. Okay? And then finally, the last thing we talked about in this chapter was the chemistry of alpha-beta unsaturated carbonyl compounds. Right? This is where we have an alkene conjugated to a carbonyl group. We used resonance theory to explain that these compounds are electrophilic both at the carbonyl carbon and at the beta carbon of the alkene. So they could react with our organometallics at either of those sites. And we learned that the Grignard reagents and the organolithiums undergo what we referred to as 1,2 addition. They will add to the carbonyl carbon, generating allylic alcohols as the product. Our organocuprates, in contrast, will react at the beta carbon. They will undergo what we refer to as 1,4 addition, retaining the carbonyl group in the product, forming a carbon-carbon bond between the R group and the beta carbon of the alpha-beta unsaturated species. So that concludes our topics from chapter 20. You can go ahead and stop it.